Good morning friends, I welcome you all for another lecture on the course Microprocessors and Microcontrollers. From last few classes we are discussing about 80386 microprocessor. In that we discussed silent features of 80386, architecture of 80386, pin configuration of 386. In today's class I am going to discuss about the register organization of 80386. We know that 80386 is a 32-bit processor. So that the registers which are present in 80386 are 32-bit registers. In that some of the registers are 16-bit registers also available. Those things also I am going to cover in this lecture. Right. So 80386 registers are divided into 7 different groups like this. The first group of registers are called general purpose registers, GPRs. The second variety of registers are segment registers. And the third variety is instruction pointer and flag register. Fourth variety is control registers. Fifth variety is debug registers. Sixth variety is system address registers. And seventh variety is tester registers. These are the different varieties of registers we may found in 80386. I repeat once again, what are the registers we have in 80386? Those registers we divided into these 7 different types. In that first variety is GPR, second type is segment registers, third type is instruction pointer and a flag register, fourth variety is a control registers, fifth variety is a debug registers, sixth variety is a system address registers, and the last seventh type is tester registers. Now I am going to discuss these register varieties one after other. I start my discussion with the first type of registers, general purpose registers. So see here friends, these 8 registers we consider as general purpose registers. Those are EAX and EBX, ECX, EDX, ESI, EDI, EBP and then ESP. Like this, these 8 we consider as general purpose registers. Next we have 6 segment registers like the CS, SS, DS, ES, FS and then GS. And the last is this instruction pointer IP and the next one is a flag register. This is some pictorial representation of the registers which are present in 80386, and here I will just only mention some of the registers. That is the first 3 category of registers. Fine. The first type I already mentioned, that general purpose registers. The first of all, which registers we can call general purpose registers? You remember friends, I already told you about the GPR. If you want to call a general purpose register GPR, that register is suitable to hold either data or an address. I repeat, if you want to call a register is GPR, the register is suitable to hold either data or an address. That means the usage of these registers are purely depends on user interest. That you have to remember about GPRs. We will go and discuss some more about this GPRs in 80386. 80386 has 8 32-bit general purpose registers. What are those 8 32-bit registers? One is EAX, EBX, ECX, EDX, ESI, EDI, EBP and then ESP. These 8 registers we consider as general purpose registers in 80386. And next, these are used to hold instruction operands. These are used to hold an instruction operands. What an operand is? If you took an instruction, the operand may be, it may be a data or it may be an address. Your operand of an instruction may be either a data or it may be an address. So that I'm already mentioned, guys, that is general purpose register is a register which is used to hold either data or analysis. And coming to the next important thing is, what are the 32-bit registers we have come across these GPRs? In these 32-bit general purpose registers, we can go and use as 16-bit registers. That means whenever my 80386 can do their operations on 16 bits, the time it didn't go and use 32-bit registers. Like it didn't go and use EAX, EBX, ECX, EDX and so on like this for 16-bit operations. The time what it does, it just go and use only a 16-bit registers. So that provision exists in case of 80386. That means I can go and use 16-bit general purpose registers to do a 16-bit operations in 80386. That means I can go and use AX register only to do a 16-bit operation, and BX register, CX register, DX register, SI register, DI register, BP register and SP register. These 8 registers I can use individually for doing of a 16-bit operations. So see here guys, once again the previous diagram. See this, I'm already told you this is our general purpose register. The total size of our register is 32, that is from 0 to 31. So if my processor can do a 32-bit operations, then straight away I can go and use these 32-bit registers for my operations, that is EAX, ABX, ECX, EDX, EBB, ESP, EDR and then ESI. I can use these 32-bit registers straight away. But whenever my processor can go and do an operations on a 16 bits, then I need not be on these 32-bit registers. I just go and use only a 16-bit registers of this general purpose registers. So in that aspect, I may get AX, BX, CX and so on SP. At the same time, my 80386 sometimes it can do operations on 8 bits. The time I didn't go and use either 32-bit registers or I didn't go and use a 16-bit registers. The time I just want only 8-bit registers. So in case of 80386, I am able to get 8 8-bit registers. That means I may get AH, AL, BH, BL, CH, CL, DH and DL. These 8 are 8-bit registers I can able to get in this 80386. Only the thing here is, friends, these are 16-bit registers I split like this. That is from 0 to 7 and then 8 to 50. 0 to 7 AX register I consider as AL, and from 8 to 15 I consider as AH. Right? And similarly this BX, BH and then BL, and this CX, CH and then CL, and DX, DH and then DL. So here it is very clear, friends, that is, if my 80386 can do their operations on a 32-bit, I can have total 8 32-bit general purpose registers available in 80386. If my 80386 can do their operations on a 16 bits, I may get 8 16-bit registers in 80386. If my processor can go and do their operations on 8 bits, I may get 8 8-bit registers in 80386. So that is an important thing regarding to these general purpose registers. That's what I have written here. The lower order 16 of 32-bit registers can be accessed separately. This can be done by using the 16-bit names of our registers like AX, BX, CX, DX, SI, DI, DE and SP. And similarly, if I want to do an operation on 8-bit, I may get 8 8-bit registers like AH, AL, BH, BL, CH, CL, DH, DL. And here one important thing, friends, that is, In case of our 32-bit registers, always we prefix a character E in front of our register name. That E represents extended. E represented extended. So if I want to call EAX, it is nothing but extended AX register. Similarly, EDX means extended DX register, and so on. ESP means extended SP register. So like this, we have 8 general purpose registers. And next, coming to the segment registers. So in case of 8086, we know that it has 4 segment registers. Those are CS, DS, SS, and then ES. But coming to 80386 processor, the count is increases to 6. That means 80386 processor have total 6 segment registers. Those are CS, DS, SS, ES, FS, and then GS. And you remember, friends, the job of these segment registers, it is not change if you are moving from 8086 to 80386. What we know about the functionality of our segment registers in 8086, the same thing we can apply for 80386 segment registers. What that a function? If you remember it, guys, the functionality of our segment registers are, these are simply used to hold the starting address of the segments, or the segment registers are used to hold the base address of the segments. Simply, the segment registers are address registers, because these registers are only used to hold the starting address of a segment, which we can call base address of a segment. So this is one thing you have to remember. And coming to the second important thing is, these segment register size are just only 16 bits. But if you refer your 386 general purpose register, their size is a 32 bit. And next one of the register we are going to discuss, those register sizes may also a 32 bit. But coming to the segment registers, these sizes are just only a 16 bits. Right, so that is a second point everyone has to remember. And next, coming to this segment register, first one is CS, means a code segment register. The job of this code segment register is always it is used to hold the starting address or base address of code segment. And coming to the second one is SS, means stack segment register. It is used to hold the starting address or base address of a stack segment. And later, you may found a DS, ES, FS, and GS. These are 4 segment registers we are used to hold the starting address of a data segment, as well as extra segment, as well as F segment, as well as G segment. That means here there are 4 segments we dedicated to hold a data, and 1 segment we dedicated to code, and another segment we dedicated to stack. But to hold a data information, we are dedicating 4 different segments. That is a data segment, extra segment, and FS segment, as well as GS segment. So this FS and GS, these are 2 segment registers additionally added to 8086 segment registers in this 80386. And one more thing, these FS and GS also considered as a default data segments. So that is a third thing you have to remember. And coming to the important thing about these segment registers is, these segment registers are used to hold the base address or starting address of a segment that I already coded. So that is only what happened in the real mode operation of 80386. I repeat, friends, don't confuse. These segment registers are used to hold the base address or starting address of a segment only in the real mode operation of 80386. But if you come into the protected mode operation of 80386, these registers are used as segment selectors. That you have to remember. I repeat, these segment registers are used as segment selectors once 80386 was operating a protected mode. So that is an important, friends. You remember, everyone. So one case, these segment registers are used to hold base address or starting address of a segment. So that was happened in real mode operation of 80386. But in case of protected mode, these same registers are used to hold a selector information, so that these segment registers we can call as segment selectors in case of protected mode operation of 80386. And next, coming to the third variety of registers. The third variety of registers are instruction pointer IP and then flag register. So first of all, we'll go and discuss about instruction pointer, and later we'll go and discuss about flag register. What instruction pointer? Again, you remember friends, 8086 concept. In case of 8086, we have an instruction pointer register IP. The job of instruction pointer register IP is, it is used to hold the offset address of a code in a code segment. That means the instruction pointer IP is used to hold an offset address for code segments. Or we can see in another way, the instruction pointer IP is used to hold the address of next instruction byte what we are going to fetch in from the code segment. So here also no change in the functionality of IP, but only the thing here is its size is extended to 32-bit. That means the 80386 processor have an instruction pointer size is equal to 32-bit, which we can call as EIP. And again here important thing is, if you go to operate our 80386 is in real mode, the time we are going to use only 16-bit instruction pointer. So that time your instruction pointer is used to hold the offset address of the next instruction byte what we are going to fetch it from the code segment. So here don't forget friends, that is this instruction pointer size is 32-bit in case of 80386. But if you operate 80386 in real mode, this instruction pointer IP size is reduced to 16-bit. The time it is used to hold the address of a next instruction byte what we are going to fetch it from the code segment itself. So that you have to remember. So, and one more point here I would like to add about an instruction pointer IP is, its a function is it just looks like our program counter PC. So in case of 8086 or in case of 80386, we didn't found a program counter PC. What's the job of your program counter PC? Generally, the job of the program counter PC was always it will points the address of the next instruction what we are going to fetch it from the memory itself. Here the same job is done by an instruction pointer IP, so that the instruction pointer IP is used as a program counter in case of 8086, in case of 386. So here my conclusion is, the instruction pointer IP is simply act as a program counter in 80386. That you have to remember. And next, coming to the flag register. This is a very important for your examination point of view also. So put more attention while learning of the flag register of 80386. 80386 have total 32-bit flag register. This is what we can call as E-flag register. That means extended flag register. So in this case, if you go and observe, the least significant are 16 bits. Least significant 16 bits, that is from 0 to 50. It is considered as a least significant 16 bits of my flag register, which may consist of all 8086 flags along with some of 80286 flags. Just so remember friends, in case of 8086, the flag register size is 16 bits. In that total we have 9 active flags. Those 9 active flags we divided into 2 groups. The first group of flags we can call as conditional flags, and second group we can call as control flags. Just you remember friends, in case of 8086, the total number of active flags are 9. These are 9 active flags we divided into conditional flags. Under this you may found 6 flags, and the second type is control flags. Under this you may found the remaining 3 flags. So those are 9 flags are present in this 80386. What are conditional flags? CF means carry flag, PF means parity flag, AF means auxiliary carry, ZF means zero flag, SF means a sign flag, and OF means overflow flag. These are 6 we consider as conditional flags in case of 8086. That we know. And remaining 3 flags we consider as control flags. What those are? Trap flag TF, interrupter flag IF, and then direction flag DF. These are 3 we consider as control flags in case of 8086. I think everyone aware of for what cases the conditional flags are set to 1 and what conditions these flags are set to 0. I hope everyone will know that. But once again I recollect. So this carry flag CF is set to 1 for 2 cases. Case 1, in addition the final carry was generates. That case your CF is equal to 1. I repeat my statement. The carry flag CF is set to 1 for 2 cases. Case 1, in addition the final carry generates. And in case 2, in case of subtraction, the first number is less than second number. That means your minor is less than subtrahend. In order to do that subtraction, definitely we need a borrow. That borrow also we are representing with only a carry. So that for these 2 cases, your carry flag is set to 1. For remaining cases, your carry flag is equal to 0. And coming to the next one, PF. PF means parity flag. This parity flag is set to 1 once the result least significant byte contains even number of ones. Listen carefully friends here. I am not talking all the result bits. I was only focusing the least significant byte of a result. If the least significant byte of a result contains a even number of ones, then only my parity flag PF is set to 1. For remaining cases, the parity flag equal to 0. And next coming to auxiliary carry flag AF. Again this auxiliary carry flag we can also call as a BCD carry, or it is also called as a secondary carry. And the specialty of this auxiliary carry is we didn't find any conditional branching instructions based on the conditions of auxiliary carry. So this is why it is a somewhat a special flag compared to the remaining conditional flags. And again this auxiliary carry flag is set to 1 for 2 cases. Case 1, in addition, the carry was transferred to bit position D3 to D4. That means in the addition process, the carry was transferring from last byte to, last nibble to last but 1 nibble. If you can't consider last nibble, the bit positions are D0, D1, D2 and then D3. And the next higher order nibble, D4, D5, D6 and then D7. What I am saying about auxiliary carry? The auxiliary carry is set to 1 once the carry was transferring from bit position D3 to D4. That means the carry was transferring from last nibble to last but 1 nibble. So this is a one case for setting of auxiliary carry equal to 1. And coming to case number 2, this auxiliary carry flag also set to 1. In case of subtraction, that was happened like this. The borrow was transferring from last but 1 nibble to last nibble. Or you can say like this. In case of subtraction, the borrow was transferring from bit position D4 to D3. In these 2 cases, your auxiliary carry flag is set to 1. So that is about auxiliary carry. And next coming to 0 flag ZF. This 0 flag ZF is set to 1 once the result is equivalent to 0. By doing of any operation, the producer result is equal to 0. That occasion, your 0 flag is set to 1. For remaining cases, 0 flag equal to 0. And next coming to sign flag. The sign flag SF is set to 1 once the most significant bit of a producer result is equal to 1. I am not saying guys, the result sign is a negative or like this. Because this sign flag is affected for both the signed numbers as well as unsigned numbers operations. But this sign numbers operations only we consider sign flag. But it is also affected for unsigned operations also. So that our conclusion is like this. Your sign flag SF is set to 1. The most significant bit of producer result is equal to 1. If it is a signed operation, most significant bit of some result or some number is equal to 1, we can say that the result of that number is a negative number. If a most significant bit of a number or a result is equal to 0, that number we consider as a positive number. So please remember friends, your SF is not only affected for signed operations, it is also affected for unsigned operations. But for unsigned operations, we need not be considered SF flag, but for signed operations, definitely we are going to consider signed flag. So what the setting condition for SF? SF is set to 1 once the result of most significant bit is equal to 1. So remaining cases, that is equal to 0. So that is about this signed flag. And next coming to OF means overflow flag. This overflow flag is set to 1 once any arithmetic operation satisfies overflow. What is overflow rule? If you do addition between two same sign numbers, the result have a different sign, which we are considering as overflow rule. I repeat my friends, if any arithmetic operation satisfies overflow rule, then overflow flag is set to 1. Then what's the meaning of this overflow rule? Overflow rule means if you do addition between two same sign numbers, the result have a different sign, then overflow flag is set to 1. I give a small example friends. For example, I would like to add sum 3 with sum 2. 3 with 2. 3 is equivalent to 0, 1, 1 and 2 is equal to 0, 1, 0. If you are observing or not, for these are two numbers, most significant bit is plus. So most significant bit here is 0. Because here these are two number sign is positive. So if I do addition with that sum 1, sum 0, carry 1 and here sum is 1. So here what happens? Your input number sign is 0, that means input number sign is a positive, but producer result sign is 1, means it is a negative. So once it is a happen, we can say that the producer result have overflow. So because here this addition satisfies overflow rule. Why we are getting this overflow? Overflow we are getting because of the magnitude bit this 1 enters into sign field. Because of that we may get overflow. I can clarify this guys. This overflow flag is set to 1 once the producer result size is greater than the destination size, you may get overflow. I repeat, the producer result size is greater than the destination size, then you may get overflow. Here that thing was happened. Here this is a magnitude bit. It means your magnitude size is equivalent to 3 bits. But to hold that magnitude in a destination, just I dedicated only 2 bits. So that your 3-bit magnitude didn't copy it into a 2-bit storage area. So that you may get overflow. So I simplify this. I repeat once again about this overflow flag. This overflow flag is set to 1 once an arithmetic operation satisfies overflow rule, or I can say in another way like this. This overflow flag is set to 1 once the producer result size is greater than the destination size. Once these are two cases, any one of these are two cases satisfies by an operation, no doubt your overflow flag is set to 1. So these are the setting conditions for our conditional flags. Either it is in case of 8086, or it is in a case of 80286, or it is in case of 80386. And next, the control flags, you may find the 3 in case of 8086. What those are 3? One is a trap flag, second one is interrupt flag, and third one is a direction flag. So these are 3 we consider as a control flags. It means these are flags influence the processor operation. That's why these we consider as a control flags. In that, first one is a direction flag DF. If this direction flag DF is set to 1, our processor was operates in auto increment fashion, or our processor was operates in auto increment mode. That means always we are going to accessing our information from lower order address to higher order address, or we are going to access your instruction from always from a lower order address to higher order address. This is what we can call is auto increment mode. That was happened only when your DF makes 0. Once you change DF equal to 1, then your processor mode of operation changing from auto increment mode to auto decrement mode. It means we are always accessing an information from higher order address to lower order address. or you are accessing your instructions first from higher order address, we are moving to accessing lower order address. This is what we can call is auto decrement mode of operation. So that your direction flag no doubt influence your processor operation. And coming to the second one is IF. IF means interrupter flag. This interrupter flag is set to 1. Then your processor is ready to recognize the interrupts which are coming from an external devices through the signal or a ping called INTR, means interrupt request. I repeat, IF is set to 1. Then your processor is ready to receive the interrupts from an external devices through the signal or a ping called INTR. Because your INTR is a maskable interrupt. So later we will go and discuss what is the meaning of that maskable interrupt or non-maskable interrupt. Later classes we will go and discuss. As of now, you remember, if IF is set to 1, our processor is ready to receive the interrupts from external devices through INTR. If you make IF equal to 0, then your processor not ready to recognize the interrupts which are coming from an external devices through the signal INTR. So this is the second control flag you may found in 8086. And next one is a TF, trap flag. If a trap flag is set to 1, then your processor operation is enters into single step execution mode. That means it will go and execute one instruction, it will produce as results to the user. Later only it will go and execute a second instruction, again it will give the results to the user, and it will go and execute a third instruction like this. That means it can't execute the whole of program instructions at a stretch. It will execute the program instructions one after another. Generally, a processor can produce a results after execution of a complete program. That means your program has some n number of instructions. It will execute those n number of instructions in a sequential fashion. After that only we can produce a result to us. But if a processor enters into single step execution mode, after execution of every instruction, it will produce the results to us. That's what we can call is single step execution mode. So your processor 8086 or a 386 enters into that single step execution mode once your trap flag is set to 1, and remaining cases its operation is as usual. So this is the 9 flags which you may found in 8086. They are set and reset conditions. Fine. And next coming to a new 3 flags are added in case of 80286 once you are moving from 8086 to 286. That is IOPL and second one is NT. One is IOPL and second one is NT. So that's what I was mentioning here. That is 3 extra new flags are added to the 8086 flags to derive the flag register of 80286. They are IOPL and NT. Don't confuse the friends here. I mentioned the 3, but here I written only 2. So that means for this IOPL, I was dedicating 2 bits. I was dedicating 2 bits. And for NT, I was dedicating 1 bit. So that 2 plus 1, there are 3 bits. So 3 extra new flags are added to 8086 flag register to get 80286 flag register. What is the 3 flags? The first one is IOPL. IOPL means input output privilege level. Input output privilege level. Generally, with the help of this, I may go and get 4 IO privilege levels. IOPL 0, IOPL 1, IOPL 2, IOPL 3. Basically, these are privilege levels provides a protection to us. So, IO privilege level 0 always have a highest priority. IO privilege level have a IO privilege level 3 have lowest priority. Why? Because if you go and take guys, this is privilege level 0 area, this is privilege level 1 area, this is a privilege level 2 area, and this is privilege level 3 area. So always this IOPL 0, this is what we can call is IOPL 0, input output privilege level 0, where we may found operating system kernel, So then IOPL 1, where we may found IOPL services. OS services we are getting in IOPL 1, And next, this is IOPL2. IOPL2 holds a OS extension that you may have found in here. And finally, IOPL3, where we may found our application programs. I have already discussed about this in past classes. Please watch once again those classes. Okay, I discussed about this. So, in order to identify which privilege level we need for your operation, that I done by programming of this IOPL bits. That is, I may choose either IOPL 0, IOPL 1, IOPL 2 and IOPL 3. Generally, IOPL 0 have a highest weightage, or it have a highest priority compared to this IOPL 3. Or I can say in another way, IOPL 0 have more secure compared to IOPL 3. That means, if a person is able to access the information at IOPL 0, he is also able to access the information from IOPL 1, IOPL 2, IOPL 3. But if a person is able to access the information from IOPL 3, he was unable to access the information either from IOPL 2 or IOPL 1 or IOPL 0. So, in order to select which privilege level we need for your operation, that I was programmed with the help of this IOPL bits. So, this is 2 bits which are newly defined in 80 to 86. And another one is NT, means a nested task. That means your operation is like this. For example, I was executing some program like this. So, somewhere else here I want some program, some subroutine. So then I shift my execution to that subroutine. But before finishing up this, I need some other tasks. Okay, so if I want this particular scenario, this is what I can call is nested operation. That means one operation calls another. This one calls this, and this one calls this. This is what we can call is nested operation. So that is indicated by this. The nested task flag indicates that the current task is nested within another task in the protected mode operation. In a protected mode operation of 80286, you may identify that one task calls another task. The same thing also applied in 80386 case also. And the next important thing is 2 extra new flags are added to 80286. Then you may get the 80386 flag register. I repeat. By adding of 3 new flags to 8086, you may get to 286 flag, and by adding of 2 new flags to 80286, you may get 80386 flag register. Right. What those are newly added flag register? The first one is VM. That means virtual mode flag. Virtual mode flag. Basically, this flag is set to 1. Then 80386 enters into virtual 86 mode of operation. Generally, your 80386 operates in 3 different modes. One is a real mode, second one is a protected mode, and third one is virtual 86 mode. Now, right, once your 80386 is in protected mode, then its behavior is completely looks like 80386 itself. That means that you can go and use all the features of 80386 effectively, and it will do their operations maximum on 32 bits. Fine. But once your 80386 is in a protected mode, the time if I want to execute some 8086 programs, then what I have to do is, I need not come back to real mode of 80386. In a protected mode itself, I can go and execute my 8086 programs just by operating 80386 like a virtual 8086. That I do with the help of this flag VM. By making of this VM bit is equal to 1, your 80386 can be operated into a virtual 86 mode. That means your 80386 just looks like an 8086. So that is an important thing. And next we have one more thing, that is one more flag that is newly defined, that is a resume flag, RF. This flag is used with the debugger register breakup points. It is checked at the starting of every instruction cycle, and if it is set, any debug fault is ignored during the instruction cycle, and the RF is automatically reset after successful execution of every instruction except for IRET and pop-up instructions. So these are different flags you may found in 80386 processor. I hope you understand what are 80386 flag register. The remaining bits what I found in a flag register of 80386, those are not defined. Those may be defined by Intel for future design processor from it. But as of now, we discuss what are the flags the flag register of 80386 consists. So I hope you understand the functionality of general purpose registers, segment registers, and thereafter we discussed about instruction pointer and a flag register. In the next class, I am going to discuss about the remaining 4 varieties of registers. Again, until that, take safe. Thank you for patient listening. Thank you very much.